let us take analysis of plane truss. Hitherto we saw analysis of beams. Now we will take up a plane truss example. Again, analysis of plane trusses. It is similar to the same steps, whatever we have indicated or we have followed in case of beams, the same steps we will follow here. So I have taken here a plane truss, a cantilever type of truss, wherein you have totally 5 number of members and 4 joints subjected to 2 joint loads. Generally in the truss there won't be any member load, it is only loads will be assumed to be acting only at the joints or at the nodal points of the given structure. Loads will always be acting at the joints. So here, as you know, plane truss is consisting of one-dimensional members which are subjected to only axial force. There will be only one internal force in each of the members of the truss, and those internal forces either it may be tensile or compressive. The tensile force we take it as always positive. Here now we will follow the first step, that is identify independent forces at the ends of element or members with element coordinates. So as I told you just now, the truss element is subjected to only axial force, whereas beam elements they were subjected to 2 end moments, M1 and M2. Whereas here it is only one internal force, that is axial force, which we take as positive. I will take this AC as the first member, so this is the first element coordinate. Then BD another second coordinate. We will take tensile force positive, this is the element force, that is the force to be determined in various members, that's only the axial forces. Then this is the third coordinate, that third force we have to determine. Then this AD force in the member, that is fourth coordinate to consider. Then force here in CB, that is also tensile coordinate, that is the fifth coordinate. So that is what is first step. Identify the independent forces at the members of the given structure. Here there are 5 members of the structure and all members are subjected to only one type of independent force, that is only axial force, and that I am identifying 1, 2, 3, 4, 5. 5 axial forces which are there in the structure, and that we have to determine. So that is first step. The PM, which we have to determine, or is PM1, PM2, PM3, PM4, and PM5. These are the truss force member forces which we have to determine. So here, E value, you can assume it to be 210 kilonewton per millimeter square, and A value, area, you can take 1200 millimeter square for vertical members, verticals, and you can take 600, yes, that's what I have worked here, 200 millimeter square and 2060. Okay. So this is 2000 millimeter square for vertical members. Area of cross section you can take for other members for verticals, and 600 millimeter square for others. So that means area of cross section for members 1 and 2, you can take 2000 millimeter square, and for all other members, that is inclined members 4 and 5, and horizontal member 3, you can take area of cross section as 600 millimeters. But that data it was missing, so that also you can take it here. So that is the first step. I have to identify the element coordinates that I have identified here. Element coordinates are only one of coordinate per member, that's only the axial force. Next, second step, we have to find the degree of static indeterminacy. So you know this is a plane trace member. The degree of static indeterminacy, it is given by m plus or minus 2j. Here m is number of members, which is 5, and r is number of support reactions. So this is a continuous wall type of support. So that means I have indicated that in this fashion, hinge. So that is here it is hinge, here also it is hinge. You can take it. Here I have written basic determinate structure. So I made it determinate structure. So for all practical purpose, this you can take it as hinge, this also as hinge, and it is suspended like this with Truss. So that means here are number of support reactions are 2 here, that is 4. Minus 2 into j is number of joints, there are 4 joints, 2 into 4, 8. So degree of static indeterminacy is only 1. So degree of external indeterminacy, it is r minus 3, that is also 4 minus 3, 1. Internal indeterminacy is 0. That means this given structure is statically indeterminate to the degree 1, and it is statically indeterminate externally only, that is E equals 1. So it is externally only, it is indeterminate, internally it is determinate. So one of the external reactions I have to choose as the redundant in order to make the structure determinate, because that is the second step. You have to find the degree of static indeterminacy and make the structure determinate by introducing as many releases as equal to degree of indeterminacy in the structure. So it is here indeterminate to the degree 1, that too externally indeterminate, one of the external reactions, that is one of the support reactions you have to remove. So I will say here, choose horizontal reaction at support B as redundant as in figure. So to choose like this, I have to make this support B as a roller support instead of hinge, which is given, and since I made it roller, this is that coordinate which I have removed. And these are all the element coordinates which I am indicating by a star, and this is the global coordinate which I have introduced, I have removed in order to make the structure determinate, basic determinate structure. That is the second step which we have to do. Then third step. Here I have indicated first step, the element coordinates, that is member forces to be determined, that is PM, PM1, PM2, PM3, PM4, PM5 and all, and there are only one redundant, that is R1, that is corresponding to this global coordinate. So those are the first two steps which we have to follow, and that I have completed. Next, we have to develop the flexibility matrix, unassembled flexibility matrix. That is the third step. So here, as you know already, so the member flexibility matrix of any member, there are 5 members, any member if you take, the flexibility matrix is given by L by JE. It's as simple as that. because there is only one force, member element flexibility matrix is L by AE. For a beam member, it is L by 6EI, 2 minus 1 minus 1, 2. For truss, it is just L by EA, axial rigidity. That we have derived in the previous classes, so that you can use it. That is the element flexibility matrix for a truss. So this is one change from the problem. The element flexibility matrix is, instead of L by 6EI, 2 minus 1 minus 1, 2 for beams, it is L by AE for the truss element, where L is the length, AE is the axial rigidity. For member 1, so L is, because it's a vertical member, L is this, so this you take height as 3 meters, length as 4 meters, so the data transmission, you take as 3 meter, 4 meter. So for the first member, L is 3 meters, that is 3000 divided by AE. A value for that first member, it is given here. Area of cross section is 2000 millimeters square for verticals and 600 for others. So you take that, as I will take this instead of 2000, 1200. 1200 into E is 210. So this is that flexibility matrix. So this particular thing I have simplified. This value you are going to get as 0.7143 into 10 to the power of -5. That is the flexibility matrix of first member. Similarly, flexibility matrix of second member, that is also having same area, because that's also vertical member. Area of cross section is this, E is this, and L is also 3 meters. So that is also 0.7143 into 10 to the power of -5. And other members on similar lines, XM3, that is horizontal member, area of cross section is, length is 4000, area of cross section is 600 into 210. So this you will get to 3.1746. 3.1746 into 10 to the power of -5. So then for other two members, SM4, SM5, that's implied members, both are equal because they are of length 5 meters. This is 4, this is 3, this is square root of 3 square plus 4 square, that is 5. So that is L by EI is 5000 divided by A is 600, E is 210. That if you simplify, you will get 3.7683 that is for these two inclined. These are the member flexibility matrices which you have determined. Therefore, total structures flexibility matrix for the entire structure, you have to add all these things along the leading diagonal and you will get it. So that is 10 to the power of -5, I will take it outside. So this is 0.7143, next 0.7143, then 3.1746, then 3.7683, 3.7683. So here it is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. likewise 0, 0, 0, 0, 0, 0. Only diagonal elements of the set. Only one K1, that is Fn1, Fn2, Fn3, Fn4, Fn5. Whereas in beams, there are two elements that you have seen. Here it is only one. Straight away you can work out. It is not 7683, it is 9683. So it is 9683. That's what you are doing. Into 10 to the power of -5. So this is my unassembled flexibility matrix. That is this third step. Develop unassembled flexibility matrix. So the next step, that is fourth step, that is generate transformation matrix. Force transformation matrix. So for that, transformation. So for that I have to apply unit load along each of the redundant. Here redundant is only one. Along this direction I have to apply a unit force and between the forces in all the members. Because this is a determinate truss, you have to apply method of joints and find out the forces in all the members, and that will be the transformation matrix. First one, because there is only one redundance, the transformation matrix consists of only one row and this 5 rows and 1 column corresponding to each of the 5 elements. That we will do it now. So first we will take basic determinate structure. So that is here hinge. Here it is a very roller. So this is the basic determinate structure. Now I have to apply the unit load along the direction, R1 direction 1. So this is R, it is R1. Only one terminal, there I have to apply the unit load. So and do the analysis of the truss. So you determine the forces in all the members. So for finding out the members forces, now this truss, it has to be in equilibrium. So sigma h equals 0, there must be a horizontal reaction there, and the given loading, of course, it is 10 kilonewtons. Here it is. Of course, that I will analyze at all. That we will do it afterwards. Now I take only this R1 equals 1. This has to be 1. So this is joint 1, joint 2, joint 3, joint 4. 3, 4. That's what I have numbered 1, 2, 3, 4. I will take the free body diagram of the joint 2. This is joint 2. There will be a reaction. Here I have applied a force R1 equals 1. This is the joint 2. There is a member force, that is F24. Here there is a force F23. This is the angle theta. So if I take F23 sin theta cos theta, that is equal to 1. F23 cos theta is equal to 1. That is the force applied. R1 equals 1 I have applied here. So that 1 I have applied. The free body diagram I have shown that is. So I put joint to satisfy the equilibrium condition. Sum of all the horizontal forces is equal to 0 if you take. I will get F23 cos theta is equal to 1, or F23 is 1 by cos theta. Cos theta is, this is theta I have taken. So this is 3 meters, this is 4 meters, this is 5 meters. So cos theta is 4 divided by 5. cos theta is 4 by 5 or it is 1 by cos theta is 5 by 4. So I am getting a positive sign, that means this force direction whatever I have taken, it is okay, this same direction, so that is 5 by 4, this is also 5 by 4, both direction, that is tension. 5 by 4 is the force. Similarly, if you take sigma y equals 0, then F24, then F23 cos theta, sin theta is equal to 0. Sum of all vertical forces 0 if I take, then F23 cos sin theta plus F24, that should be 0. So therefore, F24 is equal to minus F23 sin theta. So F23 is 5 by 4, sin theta is 3 by 5, sin theta, 3 by 5. So this you will get minus 3 by 4. So that means whatever the minus I am getting, whatever direction I have taken here, arrow moving away from the joint to, that should be reversed. Here arrow should be not moving from away at 2, it is moving towards. Here also it should be moving towards. So this force has to be 3 by 4. That is in compression, not in tension. So I have a negative side, 3 by 4. So like that, on similar lines, if I take joint 1 and take the free body diagram on similar lines, here also I have one reaction is 1. So this is the force. If I take this as F14 and this as F13 on similar lines, we will get F14 as 5 by 4 and F13 as minus 3 by 4. Similar to that, if I take free body diagram of joint 1 and apply method of joints, I will get the same forces. You can see there is 1, here it is 1 like this, these are the forces. If I apply sigma is 0, sigma is 0 here also, I will get the same thing. That means here I will get 3 by 4 and this I will get 5 by 4. 5 by. So then only either you take joint 3 or 4 and you can find out the force in that particular member, and that force will be the tensile force, and here I will get 1 as the force. So that much analysis you have to do for finding the transformation matrix. Whereas in beam it was easy, just we were taking independently each beam as separately and applying the equilibrium conditions. Now we have to do this method of joints, and that is why it is a lengthy process, the Truss analysis straight away. You can do that. Therefore, your transformation matrix, it will be force in the member 1, it is negative, it is minus 3 by 4, then force in member 2, it is 3 by 4, then force in member 3, it is 1 positive, then force in 4 and 5, it will be 5 by 4, 5 by 4. So this is that transformation matrix which I got. This much extra exercise you have to do. That is development of force transformation matrix. Then of course, fifth step, that is you have to generate structure flexibility, which is nothing but TT, KMT. So straight away you do that exercise. So that is third, fourth step, fifth step, to find excess. The excess is equal to ET Xm T. So I have determined T here, Xm here. So So TT I will take it, that's TT into FM into T. If you do that evaluation, you will get straight away. I will write this FS matrix. It will be 1.608 into 10 to the power of 4 minus 4. So if you simplify that much exercise, I have left it because you have to substitute this T, you have to write it horizontally, then this FM matrix you have to take, then the T you have to take, you have to multiply. All the three you will get that exercise. Then sixth step, this is important. So that is, again you have to do that analysis of Truss. So you have to find loads and different missions that are used to find loads and different missions. Here we don't have to find equivalent joint loads. That is, we need not fix all the members because here all the trusses they are all thin jointed one. There is no moment at all. So there is no question of finding any fixed moment. It is only all the joints are thin jointed only. So we have to do only the analysis as we have done for finding transformation matrix. Same type of analysis we have to apply and do that particular analysis for evaluating that PM star. So to find PM, so what we have to do is we have to just apply equations of equilibrium. So that is, you take the determinate structure is it is roller and these are the members we have like this. The load given, it is 10 kilonewton, here it is 20 kilonewton load, 10 and 10, because only in this step we take the given loading into consideration. Until then, it is only using geometry and other properties. So using this particular load, we have to find out the forces in all the members. That is nothing but our PM matrix. This PM matrix is nothing but the forces corresponding to these element coordinates. We have to determine. So to find PM, analyze the determinate Truss for given external load. Like this. So when you have 10 and 20 kilonewtons here, so if I find the reaction here, like this reaction, suppose if I take it like this, so this reaction which is B, A, and this is C, D. If I take moment about C or moment about A as 0, then this or B into this 4, that is like this, then this will not give any moment, only this, or 20 kilonewtons into 4, or B will be equal to 20. So this reaction, or B, it is 20. On same lines, this reaction, or A, is 10 kilonewtons. So now you take the free body diagram of support B, you have 20 and you have these members, the force in this member BD, I will take it as a BD, this has FTC. On similar lines, this, if I take theta, then FDC cos theta is equal to 0. So therefore, this FBC, force in this member BC is 0. Then if I take sigma B equals 0, this is by taking sigma H equals 0, I'll get this. If I take sigma B equals 0, I'll get this right away. FPD is equal to 20. Because this force anyway in this it is 0, therefore force here it is 20. 20 means whatever direction I have taken here, that is okay. So this is 20. On similar lines, here this has to be 10, this has to be 10, here also it is 0. Next, when this is 10, this 10, it matters, force in this is also 0. Therefore, your PM matrix will be force in member 1, it is 10, that whatever the element force which we got, that sign we have to reverse. That's what we did there. There we, in beams, we found out the fixed moment and reverse this direction. Here, we have to find the forces in all the members, and that force we have to reverse. This you have to remember. So, force here in member 1, it is minus 10. Here it is 20, though it is positive, we have to reverse this direction, and force in other three members are 0. This is the EM matrix. So, here in Truss problem, we have to do this particular analysis, basic analysis of the Truss of the basic determinate structure for given external loading, and we have to arrive at that. So, the momentum on PM, we can find out that dl is equal to Tt Fm into Em. So Fm already you have determined, T also you have determined, Tt you take it, Fm multiply it, and Pm. This if you evaluate, you will get dl as we have determined 1.60 minus 4. So where, oh, this is Fs. Fs is 1.6379. 6379. This is 1.608 into 10 to the power of minus 4. That's it. So this both are because 1.6 I get was confusing, only changes there in the second decimal. So I got that confused. So with this, we can go to last step, that is 7th step here. And that is our determination. That is 7th step. We find R hidden force. So R is given by that Fs inverse into dj minus dn. This dj is again 0 because there is no support supplement or any something is given. That is temperature variation, lack of weight if it is not given. So you can take that as 0. Only Fs inverse, it is given by 1.60, now it's 6379 into 10 to the power of minus 4, and this minus dl is minus 1.608 into 10 to the power of minus 4. This, if you take it and evaluate this Fs inverse is that. So this is Fs is this Fs inverse dl minus dl. If you do it, you will get R value as 0.9812. You get R equals 0.9812. So the moment you get R So last step, one more step I have to add it here. It is 7th, 8th step. So to find forces in all members of truss. To find forces in all members of truss. To find final forces. Final forces. So that final force is given by the actual force what we have analyzed in the basic determinate structure. This what we have determined. So the final force in all members you can find as equal to forces in all members due to determinate structure plus this R into 4T. This R into T. R into or T. So whatever T you got, that you multiplied by R. That is 0.9 something you got there, or 9812 into the T matrix. That you multiply it, add it to the forces what you have determined in the basic determinate structure, you will get the final forces. This is another extra step you have to add it to the plane truss analysis. The rest are all similar, only thing is it is a laborious process of doing the calculation. It is very simple calculation, that's only equilibrium condition, but simply it is lengthy. Except this, there is nothing much in the analysis of truss. Same procedure you have to follow, only the element stiffness matrix. Instead of beams, L by 6 here, 2 minus 1 minus 1, 2 what you are taking. Here we are taking it as L by JE, that's all, only one expression that you remember, that's all that I have wrote it out. It is only L by JE. This is for truss. As element 50 matrix. And you have to arrange a diagram, that's only one of the element. The rest are all 0. So Fm is there, yes. And afterwards, Fs computation, it is same, Tt, Fmt, that load you have to compute. For finding load, Pm, you have to do that rigorous analysis of trusses. If the redundancy is more than 3, it becomes very, very laborious job of analyzing the truss. If it is 1 or 2, you can manage. So with this, the analysis of truss we have completed. Then of course, we have only left with analysis of rigid plane frame. The two rectangular or orthogonal rigid frames is there. So that we will take up in the next lecture. So with that, whatever is there in the syllabus, analysis of beams, trusses and rigid plane frame by this flexibility method, that will be completed.